Our question today is, how does conservation of angular momentum help us explain motion? We've talked about momentum before, and momentum is inertia in motion. To think back to inertia, inertia is the tendency of an object at rest to stay at rest, or the tendency of an object in motion to stay in motion. Momentum is simply the motion part of that statement. Therefore, in order to have momentum, an object must be moving. Angular momentum is the same idea, only applied to a spinning object. So it is the moment of inertia in motion. Remember that the moment of inertia is an object's tendency to stay at rest or an object's tendency to continue moving. We're just looking at the moving parts of that inertia. Therefore, an object must be rotating in order to have angular momentum. If it's not rotating, it has no angular momentum. Angular momentum is a vector, and a vector, therefore, has a direction. As we've done in the past, we say that the positive direction is counterclockwise, and the negative direction is clockwise. The symbol for angular momentum is the letter L. And the equation is that the angular momentum is the moment of inertia times the angular velocity. And knowing this formula, we can go back here and figure out that the units should be a kilogram times meter squared per second. The unit of moment of inertia is a kilogram times meter squared. And the unit of angular velocity is a radian per second. So when we multiply these two together, at first it looks like it should be a kilogram times meter squared times radian per second. But remember, we talked about before that the radian is actually a unitless value. It's just like a placeholder. So whenever there's something else written beside the word radian, we actually get rid of it. We don't use it. And so we can see that the unit of angular momentum is a kilogram times meter squared per second. Now, one of the things we talked about with momentum is that momentum is conserved, and angular momentum is also conserved. To be conserved means that it stays the same. So total angular momentum stays the same, or it's conserved, if there's not a net torque acting on the object. So as long as there's no outside torques, the angular momentum stays the same. We can see this in a demonstration of the figure skater. I'm going to show a brief clip here of a figure skater. And notice what the figure skater does to spin faster. She's going to bring in her arms and bring in her leg. And that allows her then to spin faster. Now what she is doing here is using this idea of conservation of angular momentum. The angular momentum always stays the same number. So when she brings her hands and her leg in, it is actually reducing the moment of inertia. She is making her body closer to the axis of rotation. Now, if one value goes down, something else has to go up to compensate for it if we're going to keep the same angular momentum. So if the moment of inertia goes down as she brings in her arms and leg, the angular velocity must go up in order to keep the angular momentum the same. Another example of this would be something like a top. Not only does the amount of angular momentum want to stay the same, but the orientation of the axis wants to stay the same as well. So when a top is spinning, it'll stay upright. It always stays along the same axis. In this case, a vertical axis. If it is not spinning, it has no angular momentum, and it doesn't have to stay along that vertical axis. Same thing with a bicycle. It's very difficult to balance on a bicycle when the bicycle is not moving. But if you give it angular momentum, it wants to keep that same amount of angular momentum. Not only the same amount, but the same orientation as well. The axis of the bicycle tires are horizontal. And so as the tires are spinning, it wants to keep that horizontal axis, and therefore it's not as easy to tip over as a bicycle that is not moving.